a library that you can use to generate and verify Starks. So first, a bit of context. So the overarching goal of the library is to let you create Starks without actually understanding all the nitty-gritty details behind how Starks work. And the idea here is that you should be able to define a computation in kind of abstract and hopefully standardized way, and then the library will do the rest. It's in a way similar to how you don't really need to understand how a processor works to write Python or JavaScript code. And the way I really got into this is that I wanted to learn about Starks, and I read the white paper, I read Vitalik's blogs on Starks, and then I kind of went through his code. And to internalize the concepts better, I decided to rewrite the code in JavaScript. And also wanted to do something slightly more complex, basically, not just MIMC calculation, but like try to create a Stark that would prove a pre-image of a hash function or something like that. And as I was working through the code, two things really became apparent to me. The first one is that there is a lot of kind of boilerplate code where I was writing code that had nothing to do with the specifics of the computation that I was trying to create a Stark for. And the second thing that kind of was apparent as well is writing constraints, defining computation, writing transition function, transition constraints was incredibly tedious and error-prone process. And at least in the way I was doing it, wasn't fun to do at all. So I came up with this AirScript language that allowed me to define constraints in a more kind of, in a simpler way and in a way that could be much more easier to reason about. So kind of, the library is very young. I only started doing this maybe 4 months ago. It's still at the alpha stage, I would say, so don't use it in production yet. But it's fully functional. You can play around with it. You can go and generate Starks. You can prove them. And it was kind of easy for me because really I'm just standing on the shoulders of giants here, so it wasn't too difficult in that sense. And the tech stack for the library it's JavaScript, so you have to have Node.js to make writing in JavaScript a little bit more tolerable. I'm using TypeScript, and because JavaScript is not really that good with kind of computationally heavy stuff, I'm using WebAssembly to move some of the parts of the library and make them more efficient. All right, so today I would like to cover basically these topics. First, I'm going to give like a very high-level, very brief overview of Stark generation process, and I know it's going to be redundant to a lot of the things that you heard yesterday and today. But I think it would be kind of useful because it will show how I thought about it and how it aligns with the kind of how I broke up the library into different components. And then I'm going to show a specific example of AirScript and very simple, trivial computation, how you can define it in AirScript and how you can generate a Stark for it and how you can verify it as well. And then lastly, if there is time left, we'll show some performance benchmarks and kind of talk about next or plans that I have for the library. All right, so let's start with a Stark overview. So as you all know, Starks are used to prove correctness of a computation, and any computation starts with a set of inputs. And then if you have inputs and you have a transition function, you can apply this function to the inputs in an iterative manner, and you'll get something that is called an execution trace. And execution trace is nothing more complex than, it's a two-dimensional matrix, and you can think about this matrix as having columns which correspond to registers, and every row in the matrix is basically a state of that register at a given point in time. So once you have the two-dimensional matrix, the execution trace, the next thing to do is to apply transition constraints to it, and you get another two-dimensional matrix. And basically the way you apply the constraints is that you take, in my case, I just take the 2 consecutive steps in the library or in the execution trace, and I apply constraints to it, and then that kind of generates a row in the constraint evaluation matrix. And what the constraints do, they just verify that transition was done correctly. So you get this matrix, and here now you don't have each column doesn't correspond to register anymore. It is now a specific constraint. So if you have 5 constraints, you'll get 5 columns. If you have more or less, you'll get corresponding number of columns. So the next thing to do, you merge all of these constraints into a single composition polynomial. Now I'm skipping over a bunch of things. There is much more kind of math and logic that goes in between the steps, but kind of at a high level, you get a composition polynomial, which is kind of second to last step, so to say. And then the last step is to prove that this polynomial is of a certain low degree, and you use Fry protocol to do that. And then you get this Stark proof, which on a high level consists of 2 parts. There is a low degree proof, and then there is a proof of the execution trace. And now if we think about kind of this 4 steps in the high level, there are some things that we can notice is that, the first 2 steps are computation specific, but the other 2 steps are computation agnostic. And what I mean by this is that, let's say you have 2 computations. One is computing hash function, and the other one is verifying correctness of a digital signature, for example. Your transition function and transition constraints will be very, very different. But the way you merge constraints, the composition logic, and also the Fry protocol will be exactly the same. So that could be reused. And the way I broke it up in the library is that you have AirScript that defines transition function and transition constraints. And then you have a Stark object that has the logic for composing the polynomial into running the Fry proof, or Fry protocol. All right, so let's go this kind of step by step. So the first thing you start out with AirScript, and I'll show an example of AirScript in a few slides. But AirScript, as I mentioned, defines transition function, transition constraints. It also defines some other things like a field in which you're going to be working with. It also defines like constant and read-only registers, and I'll talk about them later on as well. And then you compile AirScript into a Stark object, and that basically generates a code that you can execute that will generate your execution trace, and it will generate your constraint evaluations. And then you can use the Stark object to generate Stark proofs for this computation. And you can generate many proofs using the same object based on which parameters you pass in. And you pass in 3 types of parameters, basically, to the proof method. The first one is secret inputs, and then you can pass in public inputs, and also you pass in assertions, or another name for those are boundary constraints. Basically, they specify what a given register should equal to at a given step in a computation for the execution trace to be valid. And then verification works kind of in a very similar manner. You start out with AirScript, you compile it into a Stark object. Now you provide a proof as one of the inputs. You still need to provide the public inputs and assertions. And then you can verify the proof whether, if it either passes or fails. So pretty simple. So let's do a very quick example. Let's say this is our computation. It's a trivial computation of sorts, but basically what it does is we have a single column, a single register, and the way we define transitions is using these 2 equations. And the first equation basically says you take the current value, square it, and add some constant to it. And the second equation says you just subtract that constant from the current value. And we decide which of these 2 equations to use based on whether the current step is a multiple of 4 or not. So every 4 steps we apply the first equation, and then in the other steps we apply the second equation. And this is how the AirScript defining this computation looks like. It's basically just about 20 lines of code, I think. And it's very small font, so let's go through this line by line and zoom in a little bit. So the first thing that you do is you kind of define what your Stark is. You give it an aim, and you also define the field over which you're going to do all the mathematical operations. In this case, it's a prime field, 32-bit modulus. At the current point in time, the library supports only prime fields, but I wrote in such a way where it's modular, and you can, if you have, if I get to writing the binary field implementation, it's just pluggable into the library. The interfaces are well defined. So once we have kind of the basic properties set up, the next thing to do is define what I call read-only registers. And these are the constants that are going to be used when we generate an execution trace and when we kind of evaluate our transition constraints. They're not really accessible, they're not really mutable by the transition function. So the transition function can use these registers, but it cannot change them. And in this case, we're defining 2 read-only registers. The K0 is going to be just those 4 values, 1 followed by 3 zeros, repeated over the execution trace, and it's going to be used to figure out which of the 2 transition equations we're going to apply. And the other P0 register, it's an input register. Basically, we don't provide values here as a part of the definition of the script. The values will be provided at the time when we generate the proof or try to verify the proof. Okay, so now we have these read-only registers. The next thing to do is to define a transition function. So as I mentioned, this trivial computation has only 1 register, so we say it's a 1 register, and we're going to run it for 64 steps. And then one thing to note here, so if K0 was a static register, R0 is kind of a register in the execution trace that holds the current value of the of the register. So what we're doing here is we're basically saying when the value of K0 is 1, then square the current state of the register and add P0 to it. Otherwise, take the P0 and subtract it from current value of the R0 register. So pretty straightforward. And then once we have the transition function, the next thing to do is to define transition constraints. And in this case, they are pretty straightforward as well. we have one constraint. And if you look here, I think I made a mistake with the exponents here, but basically it should be the out portion and the else clause should be corresponding to, let me go to the previous step, R0 minus P0. So here, like ignore the else clause, but the when clause is correct. So when K0 is 1, we kind of compute the transition function and then subtract it from N0. And N0 in this case is also a register that refers to the execution trace, but it refers to the next step in the execution trace, not the current state. So we basically say if we compute a transition function and subtract the value that we get by computing that from the next step in the execution trace, we should get a 0. And if we get a 0, then transition is valid. Okay. So let's look at the concrete example of if we run this error script, what kind of execution trace would it generate. And here, the first thing to notice, so we have our K0, P0, and R0 registers. And the first thing is in K0, you see that pattern repeating over time. So you have one followed by 3 zeros. And then I'll explain where the values for P0 come from at the next slide. They're basically going to be provided at the time when we generate the proof. And R0, we initialize it to value 3, and then the way we compute kind of the execution trace is that we apply the transition function to kind of the first row, and in this case, K0 is 1, so we square the value 3 and add 1 to it, so we get 10. The next step, we repeat the logic, but now K0 is 0, so we apply the second equation, which is just subtracting 1 from 10 in this case, and we get a 9. And then if we run this for 64 steps, we get to this 394 value at the bottom. So this is how the execution trace would look like. Now, how do you run it from JavaScript? So pretty straightforward. The first thing you do, you create the Stark object, and you pass the script into it. And the script in this case is just a string variable containing the same script that I showed on the previous slides. The script gets compiled into executable code, and then you can use the Stark object to generate proofs and to verify proofs. But before you do that, you need to specify some assertions, and you need to provide some input values. And here, the assertions are, again, boundary constraints, very simple, just saying that the computation would be valid if at step 0, the value of our register is 3, and it would be valid if at step 63, the value would be this 394 number. And here we also define the values for P0. In this case, just a sequence of integers, and those are going to be kind of stretched over the execution trace when we pass it to the proof method. So once we have that, we run the proof method, generates a proof, and then once we have a proof, we can verify it using just the verify method. And of course, in this case, the verification would pass because we just proved and verified the same exact thing. Now, what this really is basically, if you think about at a high level, what this says is that if we were to take this computation defined by these two equations, and we were to run it for 63 steps, we would get an execution trace that would basically comply with the constraints that we specified. And of course, if we, for example, before verifying, if I were to change P0 values to something else, or if I were to modify assertions, the proof would fail. All right. So this was a very trivial computation. I used AirScript to write kind of Starks for different types of computations, specifically, MIMC, and also Merkle proof, like verifying membership in the Merkle tree using rescue and Poseidon hash function. One thing I should mention that this should not be used as a comparison between hash functions. There are many different ways to fine-tune those hash functions, and I wouldn't say that I kind of spent enough time to trying to figure out what's the optimal parameters for each hash function and so forth. So take it more as a directional kind of numbers. But at the high level, what this would tell you is that if you were to use the library right now, and you wanted to kind of create a Stark that would prove a membership within a Merkle tree of depth 16, for example, it would take you about 2 seconds to prove, and the proof size would be somewhere between 60 and 80 kilobytes. One other thing that you can see here is that kind of the numbers behave as you would expect, for Starks, because as an example, if you double the length of the computation, your proof time pretty much doubles, which is to be expected because it is linear. And then, proof size doesn't grow nearly as much. This is the logarithmic portion, which is a nice property of Starks. It just grows, slightly with doubling or, quadrupling computation and so forth. If you really paid attention to the proof times, you probably noticed that for 256-bit fields, the proof times are outrageously huge. And one of the reasons there is that because 128-bit fields are actually optimized for WebAssembly, so all the math is running in WebAssembly, but 256-bit fields are running in JavaScript, which makes them almost 10x slower. Okay, so future plans for the library. As I mentioned, the library is pretty new. I've been only working on this for a few months. There is a ton of things that can be improved, and one of the big areas of improvement is AirScript itself. It has a few nice constructs, but it's not yet powerful enough to define kind of everything that I would like to define with it. So one of the things, for example, I would like to have loops that would allow to create more kind of expressive statements within the language. And I've been thinking about loops for a while, and I think I have a good sense of how to implement them in an elegant way. But more kind of like important thing, I would say, is a script composition, where the goal here is to create a structure where you can define AirScript, let's say, for a hash function, and then you can import it into an AirScript that would define Stark for a Merkle proof, and then you can import that into a different AirScript that would define an even more complex construct. And the ultimate goal here would be to make AirScript kind of powerful enough where you can write a Stark prover in AirScript, so you can basically do a recursive proof of a Stark in AirScript. And this would be kind of ultimate success if I can get to that point. Beyond this AirScript itself, proof speed can be improved dramatically. I showed you the numbers there, but I optimized some things, but not nearly enough. As an example, in the Merkle proof Starks, 80% of the runtime for generating proofs is spent on evaluating constraints, which is basically just poor optimization on my part on how AirScript gets converted into executable code that generates those matrices. Now, there is a much better way to optimize that, and if I spend some time optimizing it, the proof time would probably decrease by a factor of 2 or 3. And then kind of the big thing with Starks in general is that they're hugely parallelizable, and right now it's all running in a single thread. Moving it to multi-threaded environment would kind of give much, much more benefit to reducing the proof time. Beyond the kind of proof speed, there is a proof size, which is another important parameter. And there are a few things that I can still do on that front to improve the security of the proofs while keeping the size the same or reduce the size of the proofs. And I've listed a couple of them there. But really, in this area, I'm not the expert, so I'm kind of looking at the StarkWare guys and other people in the academic community who can come up with novel ways to reduce the proof sizes even further. So with that, it kind of covers what I want to talk about, and I'll open it up for some questions.
So what do we think? Are there some questions? Give it a second. If there are, right. The mics are just over here.
All right. Well, if other questions arise later on, find me somewhere after the conference or during the breaks.